Welcome once again to ChemSkills Podcast Suite, podcast 8 this time, and the topic for this podcast is electronic configuration of ions. Ions are charged atoms or groups of atoms, charged molecules, and they are formed from the gain or loss of electrons, not protons. When we look at the structure of an atom, we see that the protons are in the nucleus, but the electrons are around the outside of the atom. So it's much more likely that the electrons are going to be lost or gained during atomic collisions, such as those that occur during reactions. So ions are only formed from the gain or loss of these electrons. Positive ions are typically formed from metal atoms when electrons are lost. All positive ions are formed when electrons are lost. And if we look at this example with lithium, we've got the 3 protons in the nucleus, the red particles. We've got the 4 neutrons in the nucleus for lithium, and 3 electrons circling the nucleus, 2 in an inner shell, and this one on the outside in the second main shell. Now, when lithium becomes a lithium ion, it's the outermost electron that is lost, like that. Let's have a look at that again. The outermost electron is lost. And so now we have a situation where there are 3 protons left in the nucleus, 1, 2, 3, only 2 electrons left. Because the protons are positive and the electrons are negative, the resultant charge on lithium is 1+, and it's written in this form, Li+. Now, the outermost electrons are lost to leave a noble gas configuration, and we know that noble gas configurations are stable. So lithium would only form a single positive ion. To lose a second electron would involve removing one of these 2 electrons from a filled inner shell, which would require a lot of energy and unlikely to occur then during a chemical reaction. So the lithium ion is Li+. The configuration for lithium is written using the subshell configuration that we saw in a previous podcast. And for lithium, it would be 1s2, 2s1. But for the lithium ion, the 2s electron has been lost, so we'd write 1s2, 2s0. But we usually drop the 2s0, and so the lithium ion's configuration would just be written as 1s2. When we look at another example, here's magnesium. Magnesium has 12 protons and 12 neutrons in its nucleus, and it has 12 electrons in the shells around it. It has 3 shells, 2 electrons in the first, 8 electrons in the second shell, and 2 electrons in the third shell. Now, when magnesium forms an ion, it will leave behind a noble gas configuration. So that means that the 2 outermost electrons are lost from a magnesium atom. We'll just have a look at that again. So the 2 outermost electrons are lost, and that would leave behind a filled second shell and a filled first shell. So this is now a noble gas configuration. The result is that there are 12 protons left in the nucleus, but now only 10 electrons surrounding the nucleus, so that gives magnesium a 2 positive charge, and it would be written Mg double plus like that. The configuration for magnesium is 1s2, 2s2, 2p6, 3s2, but now for the magnesium ion, it's lost its 3s2 electrons. It would be written 1s2, 2s2, 2p6. Now, a special case, the transition metals, and for example, if we look at iron, the transition metal ion would have a configuration at 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. It's the 26th element, so if you tally up all the electrons in there, that'll come to 26. But what we do know, though, is that the 4s2 and the 3d6 configuration on the end, so the 4s subshell and the 3d subshell, in atoms tend to overlap. And as soon as electrons go into a 3d subshell, they cause the 4s subshell to move further out from the nucleus. So the actual configuration for iron would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. So now the 4s2 subshell is actually the outermost subshell, and that means that when 2 electrons are lost from this subshell, the resultant configuration of the ion for iron 2 iron would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So the 4s2 electrons have gone, and the resultant configuration is not noble gas configuration, but it is still nevertheless stable. And this situation applies to all transition elements. There are some exceptions to this, but generally to all transition elements, resulting in a common ionic charge for all the transition elements of 2+. Now, when we look at negative ions, these are formed typically from non-metal atoms when electrons are gained. For example, if we look at fluorine, fluorine has 9 protons in its nucleus and 10 neutrons in the nucleus, and it has a total of 9 electrons, 2 in the first main shell and 7 in the second main shell. So what would happen with fluorine would be that it would gain an electron. So we'll have a look at that again. So it'll gain an electron to fill that outermost subshell, to fill that outermost main shell. Now that main shell has 8 electrons in it. So fluorine still has 9 protons, but the fluoride ion now has 10 electrons, which means it now has a resultant charge of 1-, and it would be written as an F- ion, like so, F with a single negative. The outermost electrons are gained to form a noble gas configuration again. So now, as we saw with the positive ions, what was left behind was usually a noble gas configuration. Here with the negative ions, what's formed by gaining electrons again is noble gas configuration. So in order to form ions, the resultant ion would normally have noble gas configuration because it's a much more stable situation. So we look at another example of a negative ion, such as sulphur. Sulphur has 16 neutrons and 16 protons in its nucleus, and it has 16 electrons. There are 2 electrons in an inner shell, there are 8 electrons in the second shell, and there are 6 electrons in the third shell. So that third shell is the outermost shell. So it has a configuration of 2.8.6. Now sulphur will gain 2 electrons. There we go, we'll look at that again. Will gain 2 electrons to have 8 in its outermost shell, because the configuration of 2 followed by 8 followed by 8, 2.8.8 again is noble gas configuration. It's the configuration of the argon atom. So we know that this is very stable. This means now that sulphur, which has 16 protons but now 18 electrons, has a resultant charge of 2 negatives, so it would be written like so, S double negative, the sulphide ion. The configuration of sulphur is 1s2, 2s2, 2p6, 3s2, 3p4, but in gaining 2 electrons to form the sulphide ion, it gets a subshell configuration of 1s2, 2s2, 2p6, 3s2, 3p6, which is a noble gas configuration, as I said before, the configuration of argon. So, in summary, both positive and negative ions form in order to produce stable electronic configurations. These configurations are usually the configurations of noble gases. Thank you for listening. Please tune in again for future podcasts. Bye.